Okay, so last time we left off when we were talking about contextual bandits, and I think since the subject matter was relatively new, we're going to keep revisiting, at least in the first few minutes, we're going to revisit how it's different from supervised learning. Okay, so let me start sharing my screen. Okay, so first let me finish. So I'm not talking about learning goals today yet, because once I finish this, I'm going to revisit the learning goals for today, and then I'm going to talk about what's the objective for today. But last time I had a part which was left out, which was trying to kind of give an example algorithm for contextual bandit. And it's a very simple or at least a straightforward algorithm or a strategy. But just to recap on what we did last time, we were looking at the general idea of online machine learning setup, where you were basically working in a for loop. So where you would typically optionally get a context. So I mean, in the contextual bandit problem, you would get a context, but in the non-contextual versions, you would not get a context. So it's for loop where each step in that for loop or each iteration in that for loop corresponds to an interaction with the outside world or a user or an environment, okay, where you're making decisions. So in every step, you make some decisions, and you also immediately get back a response in terms of how your decision fared. For example, every day you could make an inventory decision of how many different items or how many quantities of different items you would keep. And end of the day, maybe you'll get a response in terms of how much profit you made because of inventory, influencing, the demand also. Because if your demand is higher and inventory is low, then you will have some lost sales. So things like that. Okay, but if you have too much inventory, then you have to keep them for the next day, and maybe there's some holding costs and so on. But at the high level, we were looking at the online learning as a way to directly talk about decisions rather than just prediction labels or things like that. Okay. And so last time we looked at an example of an online learning setup, and then we started talking about A/B testing. Okay, the A/B testing. The reason why we introduce it when we're talking about online learning is that it's really not online learning there, but at the same time it goes beyond just predicting labels, right? I mean, you're actually making decisions. The decisions could be complex. Should we go ahead with a particular feature in a software, or should we go ahead with a certain policy decision, in an organization? So whether it's a complex decision or a simple decision, you could actually make the decision in a data-driven way by actually doing an experiment. There's, of course, a cost to the experiment, which is that if you want to figure out in a data-driven way which decision is good, you need to try out in some sort of a randomized controlled trial, try out the decision on a bunch of, hopefully, a bunch of units, for example, users. And because of this randomization, you hope that the only difference in terms of outcomes for these two groups, treatment and a control, is because of what you introduced, which is the variation in the treatment. And so the treatment caused something. Okay, and so if maybe you see better performance, maybe you're better able to manage inventory, or if you're better able to engage users or whatever it is. So if you have that information, then you can say, oh, maybe my treatment or my new machine learning model, or my decision is better, and so I'm going to go with that decision in the future. Okay, so that was the pretext for looking at A/B testing. But clearly there was a one drawback there, which is that you're being inefficient. Okay, which is that generally A/B testing is backed by a hypothesis test, and at least traditionally these hypothesis tests require you to make a sample size decision a priori, which means that, oh, if you think that, oh, maybe I can get a 3% better performance because of the new treatment or the new website compared to my existing website. So if that's your hypothesis, then the 3% and some other choices like power of the test and say the control and the type 1 error will influence how long you need to run the test, as in how many users you need to try out before saying that potentially, the new website or the new machine learning model is better. And so that number, the pre-deciding the sample size, could be wasteful. For example, your new decision or the treatment or a new decision could be much, much better than, let's say, the status quo or the existing decision or control. Okay. If that's the case, then, and if the sample size is 10,000 users to be exposed per variation or for each of the decisions that you're making, then for the 10,000 users who are looking at control, who get exposed to control so that you get a number for the control decision as well, they're experiencing something suboptimal. So that was the inefficiency, and multi-arm bandits is a way to counter that inefficiency by dynamically changing who gets exposed to what. As in, for example, when I say dynamically, you think of an online setting now, back to online learning, where users are coming one by one. So you have a for loop, users are coming one by one. You are making a decision between, let's say, treatment or control or arms. In general, it's just not treatment and control. It could be many more choices that you have, let's say 5 choices. Then you get to dynamically decide which arm to play or which decision to make as users are coming. They, in the multi-arm setting, users come, but you don't see the context. But more than that, you get to play an arm, and then you get a response, which is the reward for playing that arm. Okay, so maybe that fared well. Maybe that user spent a lot more time on your website, or maybe you made more profit because you took a certain inventory decision rather than something else. Okay, so you dynamically adapt which arm to play in every new interaction. So if you go back to the A/B testing situation, you had to expose your each decision 10,000 to 10,000 users, so total 20,000, let's say, 2 decisions, 2 arms. So in the multi-arm bandit setting, you could, because you're dynamically changing, it could happen that if, let's say, the new decision is much better, maybe you end up exposing the new decision to 19,000 of those users, whereas only 10,000 of the users are exposed to the control decision. Okay, and this is something you could not have done in A/B testing. Okay? So that's the simple gist of why we're looking at multi-arm bandits. This dynamic reallocation, dynamic allocation of or dynamically choosing decisions based on what has happened before. Okay, and then we looked at 4 algorithms actually. So 3 of them you could say were working in the stochastic setting. So the first one we looked at is epsilon greedy, where we introduced the notion of why you should explore and exploit, where explore just means try out a random action, because if you're not getting information about it, you don't have a good sense of how well it's performing. Okay. So epsilon greedy was the first algorithm, and then we looked at a couple of variations. One is called UCB, upper confidence bound, or UCB1 actually. It was an algorithm which again maintained some raw means of what's the performance each arm or each decision in the past, plus some additional bonus term which takes care of that. If an arm was not played enough, then the bonus term kind of is large enough so that you eventually get to choose that arm which was not played long enough, even if its historical mean performance value is low. Okay, so that is UCB. Next, Thompson sampling was a very similar idea, but uses a very Bayesian point of view, where you maintain a belief that all arms maybe are equal, and then you get observation. So because all arms are equal, you draw a sample for the distribution on each arm. So what you're maintaining is a belief on the mean reward of each arm, and you kind of update this belief. So think of the mean, initial belief is a uniform distribution, and you pull an arm, the first arm, let's say all arms have the uniform distribution as the prior belief. You try out a few arms, you try out a few of the arms, let's say 99 rounds. Let's say there are 3 arms. Let's say you just happen to try out each arm 33 number of times. So for the 100th time, you will look at the posterior distribution of this posterior distribution of this mean reward. Okay, so although at the beginning of time it was uniform distribution for the mean reward for every arm, because you played that arm 33 number of times, you have observation. Maybe sometimes the arm gave you some reward, sometimes did not give reward, and so on. Okay, based on that, you get a posterior distribution. Instead of the uniform distribution, there will be some concentration towards the or some shifting of the distribution towards where the mean reward is likely possible. Okay, And then that kind of resolves, helps you exploit, a promising arm or a promising decision, as well as because you're sampling from these posterior distributions every round, you can also do exploration there. Okay. So that was the idea behind Thompson sampling. And then we moved on to another algorithm called Exp3. I will not spend time describing that now because we're going to talk about Exp4. And so when we're talking about Exp4, we'll talk about Exp3. Okay. So that's a very quick or a little bit longer introduction to what we did last time. So that was about bandits. Okay. So 4 algorithms there, as I said, epsilon greedy, UCB, Thompson sampling, and Exp3. And then we said, okay, that's an interesting efficiency thing you could do, and minimize what is called regret. Okay. So you're not just trying to find out the best decision, but you're also saying that when you're trying to find out the best decision out of, let's say, 3 decisions or something, you're also ensuring that you're not playing the suboptimal decisions too often. Okay. And that is captured through the notion of regret. And we saw some curves talking about, here's the regret curve as a function of the number of interactions. It grows. It looks like a logarithm of the number of interactions or something. Okay. So now let's talk about contextual bandits. In the contextual bandit problem, what happens is every round you get a context. Use blue. You get a context, and then what we want, in every round, what we need to do is when we get a context, we have to just say which action to play. It's very similar to multi-round bandits or any online setting. You just need to decide every round what to do, which is which decision to make. For example, which articles to show. But the thing is that you have a context. So because there's a context and input is a context, and you want to decide an action, that function. So you can think of it. There's a function there which takes context as an input and produces a action as an output. Okay, and so the learning part is to learn this function, and it's called a policy. And we'll revisit this notion of a policy again and again throughout this lecture. But policy is just think of it as, given a context, I want to say what is an action. Okay. Okay. So let's go through an example first to get a sense of how contexts make the problem slightly different than the bandit problem, the multi-round bandit problem. Okay. So let's say we have 5 actions. Okay. We have 5 actions, 5 ads that we can show. These are the ads A1, A2, A3, A4, A5. Okay. Now let's say we already have some policies, some candidate functions. Okay. So when I say we have 4 policies, each policy is saying, okay, if this is the context, so let's say we have 4 policies. Let's say we're talking about the first policy. The first policy says, oh, for context, let's say contexts are also enumerable. So there's only, let's say, 10 contexts. For context 1, this first policy is saying, oh, play action A1 or show ad A1. So let's say if this user is interested in likes animals and pets, so maybe this user, you know that from the context. And so the first policy says, oh, for this is the right ad to show. Okay. Maybe for context 2, maybe this user is a musician. For them, or audiophile. So you may suggest action A3. Okay, which is the ad A3. Okay. So this function, right? So there's a function which takes C as an input and produces, returns some action. Okay, A1 or A3 or whatever it is. Okay. So that's what a policy is. Let's say we have only 4 policies, and so it's a little bit fictitious, but let's say we only have 4 policies from which we need to figure out which is the best policy. Okay, which is the best policy. So while taking into account that you can dynamically switch between you can dynamically switch between switch the actions that you play so that you figure out which is the best policy. Okay. Because the naive thing to do is, because we have 4 policies, you can say, oh, maybe for the first 100 rounds, let me try out the policy 1. Next 100 rounds, let me try out policy 2, and get some measure of how good a policy is, and therefore figure out which policy it is. Okay. But that would be akin to doing something like A/B testing. But here we want to do something different. Okay. Trying to be dynamic. Okay. Adaptive. So now let's talk about, okay, so let's say we have 4 policies. What we can do is say, okay, policies are fine, and policies eventually give us actions. But let's think of these 4 policies as our arms. Okay, so we just need to decide which policy to pick in each round. And once we pick a policy, the policy itself will tell us which action to pick, right? So instead of talking of, so remember in bandits, we were thinking of actions as directly, actions would be directly the ads themselves. But let's say for a moment that instead of thinking of ads themselves as the 5 decisions here, we'll think of the 4 policies as the 4 decisions. Okay, and so in each round, you see a context and you say, oh, let's play policy 1. In the next round, you see some other context, you say, let's play policy 2. Okay, something like that. So you can do that, and if you do that, then you go back to what is the an algorithm called Exp3. Okay, what is Exp3 algorithm? It's basically maintains a bunch of weights on each arm. Okay, and since arms are policies, we just maintain a weight on each policy, maintain a number. It's basically a weight as in a score, which says, oh, if the weight is high, you can imagine that, oh, maybe this policy is actually better. Okay, and there is some randomization that happens with respect to how to pick the next policy, and we're going to discuss that in a couple of slides. So the key feature is just that you maintain weights on each arm, and you play arm according proportional to the weight on that arm. Okay. So now let's say let's look at one round to get a sense of this context, how to exploit context. So let's say in round T, we have these 4 policies. Let's say E1, E2, E3, E4. They are, we haven't picked a policy yet. And let's say each of these policies is saying, for this, so there's a specific context that came for which 2 of the policies are saying play add 2, and 2 of the policies are saying play add 4. Okay, so this one or this one, sorry, this one or this one. Okay, so now, but the this is what the policies are saying, but you just have you just have to pick one of the arms, right? So let's say you pick arm E1. Okay, you say pick policy E1, and E1 we know is already saying, oh, play at A2. You just look it up, and then you display at A2, and then wait for a response. Okay, and the response could be click or no click, and let's say it was clicked. Okay, that's good. It was clicked, so you picked an arm. There was a response from the environment, in this case a user, and they came back to us, and we saw that they did click on the ad. Okay, clicking is just an example response here. So then what Exp3 does is it has to readjust the weights now. It played an arm, and the arm somehow got a positive response. So you have to, you need to change something, which is how you play these arms, right? And the way you change it is you increase the weight on the arm that did well. Okay, so what you do is get a slightly modified score. So x tilde s just means whatever score I got. Let's say click means just 1. The slight modification is that what's the probability with which you played this arm. Okay, and we can discuss this offline why this normalization is needed. But modulo that, there's some score that you get. Okay, and then you can use the score to update the weight. So basically, there was some weight at time t. The next time you want to play the arm, wt plus 1 would somehow take into account that there was a positive score that I got for this arm E1, and for all the other arms, you would give a reward of 0, so their weights may, for example, not change. Okay, and the whole point of contextual balance is that we can do better. Okay, so we can do better, and why is that? That's because the policy 2 is also recommending the same same action or the same ad. So although eventually you picked policy 1 and eventually it showed ad A2, but you know that if you had picked policy E2, it would have said the same ad A2, and you actually showed A2. Okay, so you should just you should better estimate the reward for E2, because at the end when you showed ad A2, it didn't matter whether you had picked E1 or E2, because it wouldn't have mattered, right? Because both are suggesting the same action, A2. So your estimate for the performance of policy E2 doesn't have to be 0. It can actually be the same as the response for the performance for policy E1. Okay? And that's the key idea. Somehow you're exploiting the fact that these policies for the same context may suggest the same action. And so when when you are ascribing back, okay, some policies are better than the other because of the new feedback that you got, you can actually update the performance of all the policies which gave you the same, which would have resulted in the same action. Okay, so that's the benefit of context. You couldn't have done that. So go back to the multi-element binary setting. If you had these, or even here, right? If you had 4 policies and you played first policy, traditionally you would just update the performance of the first policy because that's the only thing that was played, and for that thing I got a reward, and so I only change the performance of that action, right? That policy. But here we're just saying that you can actually change the performance of other functions or other policies that you have. Okay, so that's the key idea. So now let's go back and talk about a simple strategy or straightforward strategy here, which is actually called Exp4 algorithm. So it's actually not very tactical, but just explicitly captures how context is being exploited to update numbers of multiple policies at the same time. Okay, update weights for multiple policies at the same time.
So do we update weights based on the reward function? You just explained that.
Yes, exactly. So let's go back here. So what, in Exp3, which was for the bandit multi-element binary case, or Exp4, what you maintain is a number, okay, a number for every decision that you take. So in Exp4, it just happens as the numbers that you maintain are for policies. Remember, policies are just functions which map from context to actions. In the binary setting, weights were just numbers that you ascribe to each action itself. Okay. Now you get, when you play an action, you get a reward, right? So something can happen. So you took a decision. In this case, let's say show an ad. The most obvious thing you can happen is somebody clicked on the ad or doesn't click on the ad in an interaction. Let's say user came, you showed an ad, they clicked or did not click. Okay, so let's say if they clicked, maybe you get a reward of 1 unit. Okay, that 1 unit should influence. So you were maintaining weights. That 1 unit influence the next weights that you'll maintain. So there is going to be some update. Okay, in terms of weights. In particular, because you got a positive feedback, you can imagine that the weight that I was storing for this action hopefully increases because that's a more promising action because I got some reward. Okay.
Okay. Yes, got it.
It's exactly, and that's what's written in this set of slides. So so you maintain weights as 1 for everything. So remember, we are only looking at policies. So you can think of policy E1, E2, E3, and E4. This set to be equal to capital pi, okay, or any arbitrary element is like little pi if you want in this notation here. And each round, what you're saying is, you observe some context. Okay, so now instead of C, I'm using X here, but you observe some context. Okay, and what you do is, because you're maintaining a number, so W1, let's say W2, W3, and W4, the 4 numbers for each one of them. There's going to be functions of time now because you're going to update these weights over time. So what you do is you observe a context and then you actually compute some mass, some score for every action. So maybe although there are 4 policies, the number of actions is 5, right, in the previous example. So you'll compute 5 such numbers. So P of add A1, P of add A2, all the way to P of add A5. Okay, and what are these numbers? It's just the average of all the weights of those policies which are predicting this action, right? For example, in the previous case, we had policy E1 and E2 suggesting add A2, and policy E3, E4 suggesting add A4, right? Then what you do is this P number is just nothing but the sum of the weights of these two, and for A2, and similarly for A4, it will be the sum of the weights of these two. And for A1 and A3, it will be, no policy was suggesting it. There's some of the weights, there's no weights there. And then you just normalize it so that it just becomes a probability mass function. Okay, ultimately, we're just constructing a probability mass function over these actions. So if there are 5 actions, whatever numbers I ascribe, they're between 0 and 1, they sum up to 1. Okay, once you have the probability mass function, you just, there's some adjustment that need to be made. Okay, that adjustment is related to essentially exploration. Okay, so you'll see that in Exp3 as well. So you want to have, there are some arms, think of it this way, some arms, their weights could be low, but that's because you have not tried them at all. Okay, so you should always try arms with at least some probability. Okay, because if you don't try some things and you keep greedily only playing those arms which have high weights, you may be in a local optima in some sense, because there could be some arm which you did not try, but you tried it only once and the weight was low for some unlucky reason. But if you had tried it more times, maybe the weights would have been much higher, because it's a very rewarding arm. Okay, so you add an extra bonus. So that is, this is basically so for example, if a1 and a3 in the previous slide have zero weights, then this part would be anyway zero, and so you at least have some probability with which you would play a1 and a3. Okay, so and so there's some formula there, but that's not very critical here. And once you make this property mass function, then you just draw an action, and you draw that action and you get a reward. Okay, because you took a certain action. Now, given this reward, as we were discussing earlier, you would have a weight. Use this reward to update it to next weight. Okay, so for each policy pi, so let's say weight for, let's say pi is a generic for e1, e2, e3, e4. Then for e1, maybe you played e1. Sorry, you played action. Sorry, you played add a2. And so sorry, you would update the weights for the policies e1 and e2 with some renormalization. Okay, so there is the same R here, but with some multiplication and division happening. But that's just something that's some fix to do with some biasness of that's some fix needed for this algorithm to be correct theoretically. So, but you can see that it's proportional to the reward. So if you keep creating rewards, you can see e to the power reward. It's a positive multiplier, and so this weight will increase basically. Okay, that's kind of what we need at this point. So is p min a constant or varies by context? No, p min is just a universe. It's just a fixed number. Just think of p min as like 0.1, okay, or 0.05 or something, some fixed number, just so that every action at least gets a chance in every round to be played, even if its weight is like pretty zero, because you don't want to miss out on some actions just because historically the weights are low. Okay, so that's the exploration part. If you go back to epsilon greedy, there's this exploration and exploitation thing where you can exploit the current best promising arms, but you also want to try out some arm which has low value once in a while, because that statistically might have been unlucky, and so you got low rewards although its mean reward is high, for example. So that's the same idea being applied here. So it's a straightforward idea. Just maintain weights on policies, which also therefore translate to weights on ads or the actions, and then you update the weights on the policies every round based on the feedback. Okay, and if you get a positive feedback, you increase the weight. If you get negative, maybe you get negative feedback, then you decrease the weight if needed. Okay. So that's about contextual balance. So this is just an example, and the point of so let's actually spend a minute before we go back to the goals of today's lecture. So since I explained contextual balance and an example algorithm, you may be wondering how is it related to supervised learning, right? So in supervised learning, you have a feature XD, right? And you get a let's say you're doing regression, so you can no, let's say we're doing supervised learning. So given a feature XD, you want to say, um, um, so given a feature XD, let's say you're taking action 80. So let's say 80 is like a label, but you also get a reward, which is indicator of whether that action 80 is correct or not, right? For example, what I mean is that you had some feature vector. I said regression earlier, right? So let's think of classification. So you took an action 80. Let's say it's a class label, okay, and then as a reward whether that class is the correct class or not. Okay, I mean, if you had, so in supervised learning, let's think of only the training part, okay, because we have to learn. So we already have xt comma 80. I'm calling it 80 instead of YT, but that's just so that I can show the difference with the contextual manage. So n is equal to 1 to n. Okay. So some training data that you have. Okay. Features and labels. Okay. In contextual balance, you have a context, which is like a feature vector. You play action 80, like it's like a, you pick a class, for example, but what you get is a little bit different object. It's the reward, okay? A reward for taking action 80 in at context xt. Okay. Now this reward, so the difference is that for this context, you played this action, you got some reward. But you would not know what would have happened if you took an action, a different action, let's say A prime. Okay, at this, so subscript index T is just for this round, but so let's not worry about it. So if you took a different action, you would not know what reward you would have gotten. Okay, but because I know the training data, okay, so let me write it as a truth here. And if 80 is correct, just means that if 80 is equal to a truth. Okay, by which mean that, so what I'm saying is that in supervised learning, you'd have feature vector. You would play, think of the training phase. You would, for the given current weights of your whatever this function is, that goes from input to output, you predicted some class, but you can immediately know whether that class was correct or not because you know the true class. So you also know if you had played a different class, whether what reward you would have gotten. So there's a specific explicit reward function here. Okay. Whereas in contextual bandits, you have the context, you played an action, you got a reward for that action and that context only. You would not have known what would have been the reward for if I had played a different action. Whereas in supervised learning training, you would know what would have happened if you change the label. Okay, so so you are in some sense, so that's why you need exploration. Okay, try out at least some different actions than the so that you get some data points, okay, some extra data points, so that your statistics work out essentially. So let's revisit this aspect again when I'm talking about RL. So these slides I'm gonna skip here because I'm gonna have the same slides in the next slide deck, and I'm
Uh,
gonna discuss them. Yeah.
One doubt. So just to confirm, so the difference between EXP3 and EXP4 is EXP4 also gives some minimum weight. There is some probability that's going to assign for different policies rather than making it to a zero.
No. So the difference, that's no, EXP3 and EXP4 are both do that, both do exploration. EXP3 is only for when there is no context. Okay.
Okay.
So this is for multi-arm binary setting,
Okay.
and this
Oh,
is for when there are contexts. But both of them maintain weights. This one directly maintains weights on actions like A1 to A5, for example, the ads themselves. This guy, you can think of it as maintaining weights on policies. So E1, which is a function, right? E1 is a function going from context space to action space, right? And
okay.
similarly, E2 is a function going from context space to action space. Right?
Okay.
So these are maintaining weights on the policies E1 to E4. That's the only difference.
Okay. Okay. So algorithmically, both function
It's
same.
exactly the same algorithm, maintain
Okay.
weights
Okay.
and increase the weights if you get
Okay.
a positive response.
Okay. Okay.
Right? It's just
Yeah.
the action space is different. I mean,
Yeah.
uh, and so in some sense, EXP4 is just for us to understand, oh, if there's context, what can we exploit? The whole point we can exploit is that maybe multiple policies are suggesting the same action, so we can improve the weights of multiple arms at the same time. Whereas here, if you play an action, you can only change the some number for this arm only, essentially, right? Because all of the other arms you got no information because you did not try them.
Okay.
Okay. Yeah. So now let's actually do one thing. Okay. Um, yeah. So Yeah, so we'll switch gears and talk about the more general problems. So I think last time I showed some sort of a set diagram where I said multi-arm bandits are as a smaller circle, and in covering them as the contextual bandit set of problems, and then covering them as a reinforcement learning set of problems. So let's look at reinforcement learning. Okay, so if you understand reinforcement learning, these other specialized problems like contextual bandits and multi-arm bandits are just sub problems there. But because they are special cases, there are special algorithms. Okay, that's what we saw last time. Some special algorithms. Okay. So let's. So what's the goal for today? So we're going to look at basics of RL. So we're going to look at what are policies and what are essentially value functions. And towards the end, we'll talk about a very classical algorithm called Q learning, which is the same idea, which over time tries to figure out what's the best action take in every context, basically. Okay. So I'm going to talk about what's the difference between contextual bandit and RL in the first 5 minutes now. Before that, let me tell you what the goals are. So by the end of this lecture, you should at least be able to appreciate what reinforcement learning is about. And a nice, I guess, way of defining an RL problem is using a primitive or using a framework. I wouldn't say framework, a nice primitive called Markov decision process. Okay, we're going to talk about what does each word here means, what is a Markov process and what's a decision process and so on, and what's a process itself. And then by the end of this lecture, you should know the basic components in any RL style problem. Okay, the basic component is going to be a policy, and we already see what a policy is. It's just a mapping from context to actions, right? Uh, we'll we'll kind of figure out what a value is. Okay, we can ascribe values to essentially context or states, and we'll talk about why this additional object is needed. Okay, values, why are they needed? And then there is going to be a couple of equations related to these values that are going to be useful for the design of RL algorithms. Okay, they're called Bellman expectation equations and the Bellman optimality equation. So we're going to look at that. So you just need to expose yourself to understanding how did we get to this equation, and what does optimality equation imply. Okay, so some of you have looked at what is called dynamic programming before in various contexts, maybe in computer science literature, or maybe even in supply chains or OR literature. This is related to that. Okay. Um, so anyway, we'll go get there and we'll talk about it. So that's the objective. Okay. So what I'll do is actually um, uh, So let me come back to these examples that I have in the first few slides. Let me come back to those examples, but let me directly jump to what is the difference between what we saw last lecture and so far to reinforcement learning. Okay, so if you think of a block diagram, you can everything is in a for loop. Okay, so this is for each time index. Okay. In multi-arm bandit problems, you take an action, you get a reward. Okay. And your objective is to figure out what's the best action. There's one single best action. Okay. You just need to figure out what is that action. Okay. Just like very similar to A/B testing. At the end of A/B testing, all the exercise, you just figure out what is the one best configuration of your website that gets you the most, some metric like engagement or whatever. Right. Now, you are in the same for loop for the contextual band setting, except that you get a what is called a state. Okay, so I'm just calling context state. Okay, it's the same thing for us. What happens is in each time index, same thing for each time index for all three of this, and this. You get a context. You look at the context and you take an action. Okay, the action leads to a reward, not just the action but also the context, because now the reward is dependent on what action you took on in what state, right? Clearly, because you cannot have just a reward which is only dependent on action. That means that the context doesn't has no relevance, right? So both the action and the context determine the reward. And that's it. So there is no, and then you keep running in for loop. So next round, next time index, you get a new context. You take another action, and the context and the action, or the state and the action together influence the reward. Okay. So you just do this again and again. Now, this is an important slide, or at least this part is important, is that reinforcement learning problem involve a very similar idea, which is that you have a state, which is like a context. Based on the state, you take an action, okay, and you may or may not get a reward. Okay, in the sense, this dotted line just means that you may or may not get a reward for this action, in the same round, or you could get a reward for this action 10 rounds later, or some arbitrary number of rounds later. It doesn't even have to be predetermined. Okay, so actions may have longer term consequences. Okay, that's the dotted line. Okay, and of course, clearly, I mean, the reward should ideally depend on both what action you took in what situation, or what state, or what context, but also the action influences what's the next state that you will see. Okay, so in the for loop, so in the first time index, you took some action because you saw some context, let's say. That because you took certain action in that context, in the second time round, the next context you see depends on what action you took previously. Okay, so there's some temporal dependency here. Okay, that's the I guess second important part. So one is that you could have rewards which can appear not just immediately, but because here the basic unit is every time interaction, it's like a one interaction done, next fresh interaction in the next round. Okay, something like IID style property holds here. Okay, there is no relation between one time index to the next time index. Here it is not the case, right? So IID is independent identically distributed properties of underlying random variables. That type of assumption doesn't make sense. Okay? And we'll talk about IID later. Okay. So now this is just a teaser. I mean, I just pointed out a couple of things, and we're going to spend a lot more time on these aspects. So
Uh,
yeah.
can you just give like a quick example of each three of them, like the example that we understand?
So I think RL is the easiest because most of I don't know if you guys, so pick any game, right? I don't know, some of you, uh, you know, so think of, let's say, a game playing agent. Okay, so think of a game as a real world, or we can actually, okay, let me give you a real world example. So let's say you're building a self-driving car. Okay, I just don't want to make humans as the agents. So humans are the ones taking actions. Let's say some software takes actions. Okay, so let's say that software is a self-driving software. Like there's some companies which are doing that. So so the state would be the environment. Okay, so at any given time index, let's say time is a discrete time. So every second you get a sense of where you are. So maybe you're on on certain road, you're nearing an intersection, maybe there's a light there, a traffic light there, or a stop board, and maybe there are pedestrians, things like that. Okay, that's the state. Given that state, what is the action that you take? So maybe there's some control actions you can take in the car. For example, you can brake, you can accelerate, you can do nothing, for example, and so on. Okay, those are the actions that you can do. Given that, you could have a reward, okay, which could be immediate. For example, your car did not get totaled immediately, for example. But you can also have a longer term reward that you eventually made it to your destination in an appropriate time. Okay, so the action that you took now may have a longer term consequence. Okay, for example, you accelerate now. That acceleration has, it's not, it doesn't get, it doesn't vanish the next time period, right? Because now you have increased the velocity because of acceleration in the next time period. Okay, so there's some dependency. And clearly the next state is influenced by what action you took, because if you brake, you're at the same state, you're kind of at the same environment in the next time period, next second, let's say. But if you accelerate, you're in a slightly different environment. Maybe you cross the intersection, I don't know. So your state changes based on your actions, right? So I have RL is clear because we're going to talk about many examples of RL. You can think of any, I mean, just for visualization, mental visualization purposes, anything to do with robotics, self-driving if you want. And there are some examples on the lecture slide, on the on our course page where people have designed software agents, basically, which can play Flappy Bird. I don't know if some of you have seen that game or any of the games. Pick any, let's say, um, something like Call of Duty or even Dota or any of these games. If you're building any artificial agent, they're essentially um, agents that have to take actions. Their actions have longer term consequences because the actions influence what is the next thing that they see and have longer term consequences in the sense of you win or lose the game eventually, or have some scores and so on. Right. So these are some examples, but these are you may say they're not very realistic, but you can apply RL to more traditional operations problems like inventory management or uh, or even modeling user behavior on apps and so on. You can do those things. Okay, that's this. Contextual balance we already saw, right? So here, all I'm saying is a user comes, like think of the MSN example, or MSN example from before. A user comes with a user profile, that's the state. You take an action, show a bunch of articles, and they click on something, right? And then you assume that the interaction ended. Okay, they clicked on something, that was the end, and you think of the next interaction being a new user coming to your same website and you showing a bunch of articles, again getting a reward and so on. So you're not staying with the same person again and again in this in contextual bounded application. Okay. You could certainly say, oh, the user stayed and clicked on this article, track this person again, there's a new state, and then therefore I'll show these new articles, then it'll become an RL problem. Okay. Because there's a dependence across states of this user profile changing over time. Now, multi-unbanned, the classical example you can think of is from a different domain, from healthcare, okay, doing drug trials. Okay, so here you have a control, a placebo, for example, and a drug, and you can dynamically change what the next patient gets, whether the drug or the placebo, and it's gonna be more sample efficient than doing a fully randomized control trial. Okay, efficient in the sense of if drug is really promising, more people will get exposed to drug. But if drug is really not promising, less people will get exposed to drug. Whereas if you do an A/B test or a traditional randomized control trial, then there will be 100 people who will definitely get exposed to drug, whether it was good or not. Is that fine?
Yeah, that made so much sense. Yep, thank you.
Okay, so so there are actually examples in the slides in the appendix of the previous lecture note, but I wanted to get to some core ideas in RL here. Maybe if we have time, we can go back to those appendix. Actually, there are appendix even in this slide deck. If we can get there, then we can discuss some examples. Okay, so let's come back to RL. So RL or any of these problems are related to decision making, and in fact, decisions are going to be sequential in the sense that there's going to be, as I said, there's a for loop, so you have to take decisions every round up to some time horizon, maybe every day, up to a year or whatever it is. Okay, and what are the main ingredients in this way of looking at problems? There's going to be an environment. Okay, just think of it as a real world if you want, or if you're Google or one of these companies, then your environment is going to be users. Okay, users responding to what you do. Maybe you show certain ads on the search page. That's your actions. So you are the agent. Google or software is the agent. You take actions, maybe placing ads and so on. Environment is going to be users who respond to actions that you take, and your action can also influence the future. Okay, so that's where I was talking about self-driving. If you accelerate now, the next environment measurement or sensor measurements that you make are going to be different than if you took brake now, right? So the two different actions lead to two different new states of the world that you will sense, or your car will sense in the next round, for example. And you can have a delayed feedback signal. So for example, again, so you could have like in games, for example, right? In video games, for example, you taking actions now has a longer term consequence of eventually did you win over, eventually did you win the game or not, right? There is some maybe incremental feedback as well. Maybe you did not die right now, or maybe you got some immediate points. But maybe if you're competing others, your actions now may have a longer term consequence in terms of you winning or losing the game, for example, right? or this is true, for example, in many real world games as well. Um, so the general idea is how to select actions, and that's what we've been looking at: how to make decisions, how to select actions. Here we care about total reward. I mean, so because it's a for loop, similar to the notions of regret and total rewards in the bandit and contextual bandit setting, we are again interested in collect as much reward as possible as we take decisions in this environment. Okay, when we have this pool of users or whatever it is. Okay. So R will provide some good answers, or at least provide a good framework to be able to make make good decisions here. Okay. So let me describe. So what we're going to do in the next 5 to 10 minutes is describe, revisit all these underlying, quantities. Like let's with starting from the environment, the agent, and goals, and so on. Okay. So what's the environment? As I said, the environment is basically seeing an agent's action. So it's like, think of the environment as a user. Okay, if you think of an app setting, and I see an agent's action, like I see the articles being presented to me, and I generate and I say, oh, here's my new state because I saw these articles. And how I'm presenting them? Because I spent time on the website. Maybe I clicked on a few things. That's how I generate a new state. Okay, so previously I had some state. Maybe I like music, and I saw a bunch of articles. Maybe I did not click on a music article. So maybe the new state is that maybe I have, my interests have moved from music to something else, maybe sports. Okay. And so the clicks would be, for example, some immediate rewards that I get. Pay attention to the time index. So AT will generate a new observation ST plus 1. Okay. So I take action AT when I see this, so I'm the environment, right? So currently I'm looking from the environment perspective. I'm in state ST. Okay, so I'm the user. I have some state. I see an action AT that the agent gives me. I change my state to ST plus 1. Okay, and I give back a reward to this guy who generated action, this person who generated the action with reward RT plus 1. Okay, so that's what the environment's job is. I see an action, I change my state and produce a reward. Okay, and we can assume, so these 2 points are just making an assumption which is called the Markovian assumption of how states change. Okay, the Markovian assumption is that the probability of, so you can think of the environment as being stochastic. For example, me, if I'm the user and I'm the environment, me changing from state ST to ST plus 1 need not be deterministic. And sometimes it could be deterministic, but the more general version is that it could be stochastic. With some probability, I change the state where I still like some music. With some probability, I change the state where my interest for music has gone down, for example. So the probability of me going to the next state, given all the states I have states I'm going through so far, only depends on which previous state I was in. Okay, so if the environment behaves in this way, the environment is called a Markovian. Okay, Markovian just means memoryless, where you say, oh, it doesn't matter how you got to how you are in the state. The only thing matters is the state. What were the previous states which led to you coming to the state don't matter. Okay, so basically these previous S1 to S2, S3, ST minus 1, they don't matter. You can drop those random variables if you think of them as random variables. Okay. We also assume that everything is observed in the sense that if ST is a state, let's say it's the interest, and some coordinates. So think of the states as like some vectors, right? For simplicity. If they're vectors, it's as if, all these vectors, coordinates, you can observe. You as in not the environment, maybe they're observable by the, not maybe, sorry. These coordinates should be observed, should be visible to the agent, okay? If they're not visible to the agent, how would the agent know that there's a coordinate which is missing, right? There is a relaxation of this. It's called partially observable environments. Okay, and appropriately some techniques change, but it's a more general setting. Okay, but let's, for simplicity, just keep that, whatever is my state, if I'm interacting with an agent, or in this case some software or some algorithm, they can see my state. Okay, now let's come back to the age. Yeah,
in RL we assume the previous states. That was the assumption we just talked of, right? So
yeah. So our assumption, come back to this picture, is that in a state, if I take an action, that will influence the next state. That's the core assumption. The next round. Yeah.
Yeah, but in here we are taking it as an independent, as in we don't rely on the past. So isn't it contradicting?
No, we don't rely on the distant past given the current state. So all I'm saying is, given the current state does influence the previous state.
Okay,
Right?
so it is the current and future, and there's no past. Okay.
Yeah. Precisely. That's the Markovian idea, right? So given the current, given present, past is uncorrelated with the future. So the future only depends on current, basically.
Okay.
Past
Okay.
can be removed if you have the current.
Yeah, got it. Got it.
Yeah. So let's come to the agent's perspective. So what does agent do? Agent basically gets to observe these things, which is every round, oh, did I get a reward? And what's the new state that the environment went into? Okay, like, and note that these observations are not identical and independent. Okay, independent and identically distributed random variables. Okay, by which I mean that. Precisely this dependence, that my action influences which state you go to. Okay, so the state st plus 1 is not independent of which state, for example, I was in at st. Okay, so if my st is, let's say, states represent moods of your user on your app, let's say Spotify. If my mood was happy in the previous round or previous interaction, or when I open the screen, maybe the next minute when I open the screen again, I'm probably still happy. Okay, so there's no independence of my state from t to t plus 1. Okay, so that's what I mean by not IID. Okay, that's where things fall apart, because if you think back to supervised learning, whenever you have pairs where states are essentially feature vectors, and you're trying to predict something, you're trying to predict an action to take. Those pairs, state and action pairs, they were kind of independent. So for every state, there's an action that you just need to guess the best action, and you're done. But here, for a state, if you take an action, the next state depends on what the previous state was. So there's this correlation. Okay, and not just the next state doesn't not only depends on what is the previous state, but it also depends on actions. But we're not introduced actions yet. So we have not. So here I've removed actions, but you can condition it on actions as well if you want. Current action. So all I want to say is that there is no IIDness, from the get-go. Okay, and in fact, probably there's not going to be any IIDness in general. Okay, whenever we do any estimation or any learning, we have to cope with the fact that things are not IID in general. Okay. So agent's objective is to, as we discussed earlier, it's to maximize the rewards that it's collecting on average. Okay, similar to the bandit and contextual bandit setting. Even for those settings, the objective was to say that on average I perform as good as hindsight, or so that was the notion of regret. But in general, on average, I want to maximize the expected rewards across the number of periods that I have in terms of interaction. Okay, with the environment. So that's just expectation, and sometimes you can have an extra factor called a discount. Okay, it's just a number. So gamma, just think of it as a number. Let's say 0.9. Okay, all it's saying is I want to maximize the expected. So here now there are random variables. I took an action AT, I got reward RT plus 1. Plus, I went into some other state. I took an action, let's say 0.9 times. I was in some other state S1. I took an action A1, and I got a reward RT plus 2, and 0.9 square times RT plus 3, and so on. Okay. So I want to maximize this objective. It seems very messy, when I write it this way. But all you just think of it as like I just want to accumulate as much high rewards as possible, okay, over a period. Okay, the period I put dots here, but you can just think of it as over 100 rounds, 1,000 rounds, something. Okay, so this discount is just trying to ensure that when I take an action, maybe I don't care when I'm at time t. I don't care too much about what rewards I get later, too far into the future. Maybe I care about immediate rewards a little bit more. So this discount factor is just some sort of a trade-off. It's very similar to this, very similar to this trade-off between the regularization factor and regularization term and the loss term, right? So some trade-off factor. Okay. And why is it 0.9, and why is it has to be between 0 and 1? Is just because numbers work that way. If you have factors like that, then the sum is not running away to infinity, basically. So we'll revisit this if needed later. And as I said, the agent's actions influence what it sees in the future. Okay. If I break now, I'll see a different environment. If I accelerate now, I'll see a different environment. And of course, if I turn left, I'll see a different environment than if I take an action which is turn right. And another key point that you will not have seen before, as in we have not seen before when we're talking about contextual balance, is because of this temporal dependence. Maybe it's better sometimes, and we'll see it's better to trade off current reward. Maybe it's the action that you take now. You had two options, let's say action 1, action 2, and action 1 would have yielded a much higher reward, immediate reward, than action 2. But maybe it's still worthwhile to take action 2 because that will influence the next stage that you'll see where you could get much higher rewards. Okay, so there's this longer term. So you may take an action now. So think of it in this way. So I know some of you might have played chess or Go or these types of board games. You may take some action now, anticipating that you'll be in good positions later on. Therefore, you'll do better later on. So that's the trade-off that you will not see earlier. We haven't seen earlier with contextual bandits or generally bandits, and that's somewhat new here. So now let's talk about a few other components. I was talking about rewards quite a bit, and I was using this letter R, let's say RT plus 1 when I take an action AT at state RT. So, or let's say RT. So these are all random variables. It's just a scalar number. Okay, it could be positive, negative, whatever. We'll see. Generally, it's random variables, but they could also be deterministic numbers, for example. And it basically indicates how well the agent is doing it at a given time step. Okay, and the agent's job, as I said, is to maximize the sum of these types of numbers. Basically, you get one number per time index. Each time index is just a random variable because they have, if they're not realized yet, and so you take an expectation. Okay. And a key hypothesis, and this is more, I guess, gets into more philosophical aspects, is that all goals can be described by maximization of some, cumulative reward. Okay, in this framework, at least. So if for all tasks where a software has to perform a bunch of actions to get to some goal, you can somehow condense that into figuring out some reward signal, which is a scalar number at every time period, for example. So every time index. But anyway, this is not very critical. So I'm saying is the reward is basically just a scalar number. Now, let's talk about the goals. As I said, we need to select actions to maximize the total reward. And I've added the future because when you take actions now, as I said, could be this trade-off, right? I take some action now, anticipating that I could get better rewards later on. I could be in different states and therefore get better rewards. Okay. So, so which is exactly here, that actions may have long-term consequences. Rewards may be delayed, and this is again something that we did not see in the contextual balance setting. For example, I send so think of email marketing, right? So I observe the user state, and I send them an email. Okay, but the impact of that email eventually on them maybe renewing the subscription or something like that, that's 10 days later or 15 days later. So that's the reward actually, because the action you took, which is to send an email reminder or something to them. So there's such delays here. Okay, so and as I said, there could be it could be better to sacrifice immediate reward to gain more longer term reward. For example, here's a classic example, right? Many of you are doing that opportunity cost, in the sense of you are studying now and you're foregoing some reward, which is the pay if you're working right now, with the hope that you land in a state where you have where you'll have better or different skills, for example, skills in data science and so on, so that you can get more more reward in the future, right? So very, I guess, very rough example there, but you get the idea here. Okay, so now let's look at just the interaction. So basically, the agent, the environment, agent sends AT, and first I get to see, if I get to see the current state, so let's say ST, and I will also get a reward, but I can use ST, RT, and all the information that I've seen before. So maybe ST minus 1, RT minus 1, and all that stuff, maybe in the past, and then I take an action AT. Okay, if I take this action AT, if I take this action 80, the environment, for example, a user or the actual real world or whatever it is, will show me a new state and give me an immediate reward. Okay, this immediate reward could be nothing. For example, it could be 0 for now. I could get some reward later on that is related to this action. Okay, so I play 80 and I get these two. Okay, these two new pieces of information. So that's what, and that's what this is a for loop here. 80, 80 plus 1, 80 plus 2, and so on. And hopefully you take better and better actions as you move forward in time. So let's look at what's the difference between, again, RL and supervised learning. As I said, let's think of, so when we talk about in the comparison, you have to think in terms of the training phase only. Okay, in supervised learning, as I said, you have some X as the input, and so at training phase, you actually have Xi, let's say Yi. Okay, you have this pair. Okay, I is equal to 1 to n. So you have this pair of data, right? Features and labels, and I'm trying to find a function which, of course, tries to approximate. So f of xi hopefully is close to yi. That's what you try to approximate. And your reward is basically how close this f of xi is close to yi. So if you happen to have a current f which happens to produce f of xi to be very different from yi, then you lose a lot. Okay, so your reward is low, but if f of xi is very close to yi, your reward is high. Just think of reward as the opposite of loss. So if loss is high, then reward is low, which means that you're doing pretty bad. Okay. Whereas in RL or even contextual balance, as I said, you're in some state. Let me not put I there. So let me use T. You take an action. I'm using YT, but you can also use AT. Okay, or capital letters here instead of X. I could also use S here. And then you get because you took in this state, you took an action 80, you get a reward RT plus 1, and you'll also get the next state, let's say XT plus 1. Okay, you get both. So let me put an arrow here. So in that sense, it's not IID, right? In the supervised learning case, first of all, there's no relation between XI and XJ for any two pairs of examples. So here there's a dependence, and this reward signal also is more general, right? So because here the reward signal is just determined by your loss function. So you determine, once you give your loss function, you can always say, oh, instead of f of xi, if I had done a slightly different prediction, how would my loss be? But here, you don't know. You played action 80, you got a reward RT plus 1, but you don't know what would have happened if you had played a different action. Okay, so in that sense, it's a little bit more general. So let's actually now come back to, in the next few minutes, what we're going to spend time on is the basic ingredients which help us think in terms of a solution for the RL problem. Okay? So remember, RL problem, we have to maximize the total cumulative gains or total cumulative expected rewards. And that's essentially boils down to us taking good actions every round. And there has to be some learning. So for us we need to know something about the environment, right? It's like environment is like an API where we input something, we get back a next state and a reward. Okay? Based on those that signals, we need to get a really good sense of the environment and therefore take good actions. Okay? That's the learning part. Yeah.
Wouldn't there be an optimization technique like gradient descent that we try
Yes.
to label, fit in a proper f of x in SLK?
But yeah, here, yes, exactly. So here you can think of gradient descent or whatever things that you've been doing in the first 3 assignments, right? So it's exactly this.
So we don't get to see that in RL? Is it
yeah. So first of all, RL, I guess one more point that I did not emphasize this time is that, of course, this is online ML, right? So this is different, right? So here you had the full data set that a priori in the training phase. Here, you start from, let's say you start interacting with the environment, you start collecting data, okay? And this data is dependent across time. This is, for example, the feature vectors that you see, it's like the time series. If you just look at the feature vectors, xt plus 1 could depend on xt, and xt plus 2 depends on previous one, and so on. But there is a learning. So when I get to xt plus 2, and I want to figure out an action, let's say 80, let me use 80. When I'm trying to go from here to here, there has to be some function, right? So let's call it f prime for simplicity. I'm going to learn this function. Okay, so there is going to be some something like gradient descent. Depends on the algorithm style. Okay. So which is going to learn. So basically, what does learning mean? So think of everything that has happened so far. So let's start with the state S1. Okay, so we were in state S1, which let's say the self-driving car was at in a given in the parking lot. From there, we took an action. It went to S2. From there, it took an action, and so on. Maybe all the way to um, AT and maybe ST, which was my destination. Okay. Similarly, next time I again draw this car. So I have again S1. It's a different sequence, maybe A prime, S2 prime, A2 prime, and so on. Okay. Maybe it's to some other destination ST prime. This is my data now. You can think of at any given point of time. Let's say I wanna make a decision here. Okay. So to some decision. What's the decision to be taken at time t? I can use all this information somehow to be able to make this decision, and that's what that function will do. Some function different. So it's going to help me. Of course, I'm not going to use all this information only once. I mean, at any given point of time, I have to use all the information from before to figure out what's the next best action to take, right? So we're going to do that. Okay, but it's not going to look like gradient descent. Yeah.
F prime would be changing, right?
Yeah. So the whole point of learning is just like in F, right? So when you do gradient descent, you're changing the parameters theta here. Similarly, this F prime's parameters would change every time period, even if you want, or it could change. You can just figure out when to change because that additional part is only because you're doing something online.
Yeah. Okay. Yeah, it's clear.
Okay, but before we talk about this changing Fs and so on, the learning part, let's talk about just the ingredients of AS, which can describe a solution. Okay, so remember, a solution is a policy, which says in every state what action to take, and that's the first ingredient. It's a behavior function. If you tell the agent here's a policy, then the agent will just follow the policy. In this state, I should take a certain action, or maybe in this state, flip a coin, or maybe if it's a randomized policy, for example. In every state, you'll have a distribution over actions, and you can pick an action, for example. That's one component of a solution or an RL agent. Similarly, the second component, also by the way, these components are not all necessary. These are all, primitives based on using which you can create solutions. Okay, solutions just mean define the RL agent. Okay, which takes actions. The second component is called a value function. Okay, so an agent can do some intermediate processing. Intermediate processing is something internal to it, where it can evaluate what is called values. Okay, and we're going to spend a few minutes on values today. Values are just the agent can get a sense of how good every state is. Okay, some sort of goodness measure for every state. Okay, or goodness measure for every state and action, if you want. There are two types of value functions. So an agent can internally maintain these scores of how good every state is or how good every state and action is, and those scores will help the agent to do the same thing, to do the thing that it's supposed to do, which is to figure out best action the action to take in the current state. Okay, so value functions help. I think of them as intermediate quantities, which help me again to do the same thing, which is figure out the action in the current state. Okay. Similarly, a model. So an agent can actually think of a self-driving car. It can have a model of how the road network of the traffic, traffic, or how the environment may change as if I do some action, for example. That's a model of the environment. Okay. For example, some of you might have seen simulators, right? There is a flight simulator or a road network simulator, or like if you think of any of these games which are about driving and so on, they're essentially simulators of the real world, right? So an agent could have a representation of how the environment changes, and if it has a sense of how the environment changes, it can again take an action. So these are all objects that the agent can use. Certainly, the agent has to produce a policy at the end of the day, but it can also have intermediate things like values, or it can also rely on a model of how the environment could change. Its notion of how environment can change as a function of actions. Okay, so let's talk about policy quickly. So policy, as I said, is just a map. It's just a function which goes from a state to an action. So let's say little s is a state. Then pi of s, pi is, let's say, the policy function. So instead of f, I'm using f prime, I'm using pi here. its output is going to be an action. Okay, that's if it's a single output, it's called a deterministic policy. Instead, sometimes pi also represents a conditional probability. Okay, saying condition on the state, I'm going to describe a distribution over actions, and then you flip a coin and pick one of these actions. Okay, according to that probability. Okay, so that's called a stochastic policy. Um, why is there a need for a policy or an agent to behave a little bit randomly? Think of you need that randomness if you need to explore. Okay, just think of go back to bandits and conditional bandit settings. Remember, we are having this extra p min or extra like in epsilon greedy, there was this epsilon parameter which would let me do something else. That essentially is like capturing this idea of a stochastic policy. Okay? With some probability, you will take some other action. Okay, in this case, there's a distribution over all actions. So if you want to apply a policy, you can actually vary the policy. So vary the action that you take. Okay, but that's for learning. But you can also have a stochastic policy even as the optimal policy, as the policy that the agent should always use. Even after you learned even after you learned the best policy, could be a stochastic policy. That makes sense. For example, in some competitive environments, you may have to randomize. All right. So for example, if you're playing rock paper scissors, and your policy is exactly, there's no state here, but if your policy is exactly, play something deterministically, then you'll not win. Right. Anyway, there's a bit of stretch between what I'm saying here and a rock paper scissors game, but all I'm saying is sometimes policies could be, the optimal things to do could be a little bit randomized. Okay, let's look at, I think people, you already understand what a policy is. It's a mapping from state to action. So here's an example. Think of this 2D maze, basically. And here I wanted to illustrate just what how a policy would look like. So let's say, so there's a 2D maze. So what are the states here? States are going to be agent's location. Okay, so I have to, so what's the goal here? The goal is to go from start to the goal or the finish in the shortest possible time. The agent has 4 actions: north, east, south, west, and the reward is -1 per time step. Okay, this is some example. Okay, it doesn't have to be this, but if this is a reward, this is action, this is a state. State transition is if I'm in a certain state, let's say this state, and if I take a east action or going to the right, then I'll just go to the right. Okay, so there is no stochasticity in the state transition. You just actually exactly follow the direction. So in that case, what would a policy look like? Okay, a policy is, as I said, is a mapping from state to action. So every state you just have to say, what is the action that you're going to take? Okay, so for example, if you focus on every cell here, the white thing is a state. And every cell I'm saying, oh, should I go north? Should I go east? Should I go west? Should I go south? So if once you specify that, that's an example policy. Okay. Some policies are good, some policies are bad. For example, this policy seems to be good because it's at least going, it'll get you to the goal. Okay.
So the policy function is just some like search algorithm like A star or DFS or BFS that will
No. A policy is just a function. Okay, just like in supervised learning, there's a function which takes an input and produces an output, right?
Yep.
A policy is just taking a state and telling me what's the action. Okay.
Yeah,
How do we get to a good policy? There's some algorithms. Okay, and all this A star and so those are all different algorithms anyway. You'll see that to get to this policy, you can rely on some ideas in dynamic programming. So maybe we can talk about it that time. Okay, a policy is just a function. Okay, there could be many policies, right? So some policies could have an opposite direction here. So you can see there's some combinatorial explosion in describing many policies here. But policy is just a function. Okay. You optimize our policies, and that optimization aspect or searching for best policies could be any algorithm. Like although A star and BFS DFS are something different, but they're algorithms. Okay, so you can have an algorithm to search for the best policy, just like STD is used to search for the best parameters in supervised learning. Similarly, you need an algorithm here. Okay, so now let's talk about value function. So what is a value function? A value function is a prediction of future reward. Okay, so this is as it says, it's a function, but you can just, let's say if I only had, let's say 10 states, then you can think of value function as just a collection of 10 numbers, okay? One number per state, okay? So to be specific, a value function is a function which takes state as an input and produces a real valued number as an output. Remember, policy is a function which takes state as an input and produces an action that you're supposed to take. Because once you specify the policy, the agent is done. I mean, it will exactly do that action, and you may get some rewards, okay, some performance of that agent. Here, a value function is just an internal, quantity that you could potentially keep. It just says, oh, how good is how good is the state, and the goodness is measured by how much of future rewards I can get if I'm in this state, okay. So it's basically a function which maps from states to some real numbers. And in fact, you can see, let's say my policy is some fixed policy, pi. Okay, I've already committed to a policy. So which means that, if the policy is already committed, then the agent just has to execute the policy and explore, and work in the environment, and hopefully it'll reach its goal, collect some rewards and so on. But given the policy, you can also specify some of these intermediate numbers, and these numbers are actually useful later on. We'll see, and these numbers are basically, if you tell me the policy, it's just the expectation given that policy of all the future rewards I can collect from that starting state. Okay, so given the state a little less, if you tell me the policy, an agent can just keep following the policy all the way to hopefully reach the final state or some desired thing. After some rounds, if you let's say terminate, then starting from that state, because I told you the policy, you can keep following according to the policy. Maybe if the environment is stochastic, you'll see that there's going to be a lot of trajectories, right? Because the next state is not deterministic. Then you just average out those numbers. Okay, there could be some trajectory. So starting from the state S, there could be some trajectory which says, which maybe leads to end, basically with goal, some other trajectory which leads to goal. So this is all time index, and so these differences just mean that they reach different states. You just average average the rewards that you get. Okay, that's this expectation here. Okay, for each essentially what it's called a rollout, but each trajectory that you go through, you just get some rewards, and for each trajectory there's going to be a cumulative reward. Just average them out. Okay, and so that's the value of that. That's the value of being in that state. Okay, so some states are highly valuable, clearly, because from that state, if you look at the the total future reward you can collect, maybe it's high. For some states, it may be quite low. For example, let's look at this picture. Okay, in this picture, each white cell represents a state, right? So if I'm in this state, okay, the value of the state is -1. Okay, why is -1? Is because so value of the state, given the policy that I showed earlier, in that previous in the policy, I had to go east or to the right, right? So if I'm here, this state is good, because if I'm in this state, if I follow the policy, it's a deterministic policy here, so I only go to the goal. I spend only 1 unit of time, so I have a negative reward of -1, right? Um, so there's no need for expectation. There's only one. There's deterministic transition, so there's no expectation needed, and I'm already at the goal, so my reward is -1. Okay. Now, if you're here, the value of being in this state is quite bad, because if you're here, you're already in a bad situation. So you have to first of all unwind yourself, undo all the bad things that have happened to you, and reach the goal. And recollect that every moment you spend in this maze and you're not at the goal, you lose a point. Okay, every second, every time index that you spend here. So that's why the value of this state is quite bad. So you're just comparing. You're able to compare states of which state is a good state to be in and which state is a bad state to be in, and you'll see where it will be useful later on. Okay, it's just an intermediate number that you can keep for every policy. I mean, this will be useful when you're trying to optimize for policies, right? So if you can get a sense of values of states for every policy, then maybe you pick that policy which gives you really good values for every state, for example. Okay, so we'll see what's the use later.
So can we think of the state value as some kind of a target value? I mean, not all the state values are target, but there will be a particular, like in this case, there's a -1. So we can target to that state, and we would optimize our function to reach that value over time.
No. So let's not mix things. So pi is what you want to get at the end of the day, right? It's a mapping from states to actions, right? Pi of s is equal to a, or the right way to notation wise is some state set, so some action set. Okay, it's a function. Now, what are these values? They are some intermediate numbers, right? So this is again a function. So v is a function from state set to some real numbers. Okay. Uh, Actually, yeah, v pi. Let me put v pi there. Yeah. So if you have a specific pi, you can compute this. Okay, there's some computational procedure to compute this. But in terms of improving or learning, okay, it's at this point not clear how you're gonna use these values themselves. Okay, we will talk about learning later. Okay, when we're gonna, so in learning, what we're gonna do is we'll start with some, naive policy, and hopefully eventually we'll get to pi, good or pi best or whatever you want to call it. Okay, but for each pi you could have a value function. Okay, for example, at this stage, just think of it this way.
Okay. So is it good? Is it safe to assume that we would like to go to a state which has a value of -1, or?
Yeah. So you would prefer to be in those states which are good, certainly.
Yeah.
Certainly.
Okay.
Yeah. So in this case, yeah, I want to be in the state which is -1. If you compare these two states, it's better to be in this state than to be in this state. Okay, that kind of tells you that which direction you want to go, for example.
Okay.
Yeah, but we haven't gotten to the Here we are already saying we know the pi for which we are computing states, computing values. So in some sense, what you said was earlier was a little bit circular. But we're going to revisit this anyway. I think we can design that later. Last primitive component. So we talked about policies. We talked about values. The next thing that we want to quickly talk about is a notion of a model. Okay, a model is a model of the environment here, because remember, an environment is in some state st. I as in the agent place action at, and the environment changes state from st to st+1, and also emits a reward rt+1. Sorry. So those you can actually explicitly capture them as some sort of probabilities and of course the corresponding random variables. Okay. So and here in this slide, I'm just saying that all those probabilities and random variables, you can represent them using the script v and script r notations. Okay, they just mean that, oh, if you're in state st and you took an action at, there's some probability which you'll get to st+1, right? So with some probability, the st+1 is going to be some specific value for the new state, which is s prime. Okay, if you are in state s and you took an action little a. Okay, so that's a conditional probability. You can just compactly represent it this way. Okay, and because you will have many such things, right? For example, if you're in some other state into some other action, there'll be some other next state that you'll get to. So it's just a description of that object. Okay, and that's actually considered a model, because that's a description of the environment, right? If you had this, you don't need if you had this, you don't need anything else to represent the environment. Okay, you don't even have to talk to the environment, because you know exactly, oh, if I'm in this state, if I'm in this action, I'm going to get this reward. If somebody tells you these numbers, okay, maybe this happens with probability 0.6, for example, right? The second part of describing the environment is that you can also have, oh, if I'm in state, if st is equal to little s, and if I take this action little a at time t, then the average reward expectation is over this random variable. So the average reward that I get, that can be denoted using this notation, script r of s and a. Okay, it just depends. So it's just saying, dependent on the state and action, there's some reward. Dependent on state and action, there's some probability which I'll get to some other state s prime. This is just a compact description of what the environment is, and this is the only thing that's relevant for us while thinking about, oh, what's the best policy, how to maximize rewards, and so on, total rewards, and so on. Okay. So let me show this through an example. So what's the model here? So let's say this is our slightly modified grid or a maze. Okay. So here you can look at, so here what I'm showing in each cell is the instantaneous reward. So R at a given state S, taking action, any action A. So actually here the reward doesn't depend on what action you took. Maybe let's say you're in this state, okay, so S is specified. Whether you take left, right, top, or down, the instantaneous reward that you get is exactly equal to -1. Okay. Of course, if you take, let's say you're in this state here, if you take a step backward towards not reaching the goal, certainly it's going to affect you in terms of how quickly you can finish the goal. But the instantaneous reward that you get is -1. More, every time instant you're not in the goal, you are penalized by -1. Okay? So that's this reward description here. And the dynamics of the state are very simple, right? So if you are in this let me use a different color. So if you're in the state, let's say, and you move left, okay, then the next state is t plus 1 is exactly, so this is, let's say, cell number 4 and cell number 3, then st plus 1 is exactly 3. If st is cell number 4 and action a or at was equal to left. There's no probability here. With probability 1, you'll exactly be in the state which is cell 3. Okay, so that's the transition model here. Okay, in this example. So it's actually not a probabilistic example at all, clearly, because this is a fixed number and this transition is deterministic. But you can make it. You can change this maze game where, for example, if you take an action with some probability, you'll land up somewhere else because maybe there's a wind blowing on this in this maze or something like that. So this is an example of how a model is specified. Basically, this transition probability function and a reward function, immediate reward function. Okay, so we saw three things: policy, phi of s. We saw values, or value function, which is v of s, and a model, which is p, state to state prime. And state to state prime given state in action, and reward in a given state if you take an action E. Okay. So these are the three things that we saw. Any questions at this point? If not, let's take a break for 10 minutes and resume at 5:15. Okay, so welcome back. So what we're going to do now is look at the notion of a MDP, and then you'll see how we'll be using the notion of a policy, value function, and as well as the model. Okay, and we'll see how those three are related. And we'll start with, so there's a sequence through which we can understand a Markov decision process better, and it's going to be a good model of how to model an RL problem. Okay, so we'll visit, as I said, we'll look at policy, we'll look at a value function given a policy, and the model as well. So the objective for this section is not to really, again, optimize for the best policy yet. We're going to do that once we tie these three things together. So far, I've introduced, okay, value is some sort of a goodness measure of each state. Policy is exactly what it says, and there's the notion of model. But they're all related to each other, right? Clearly, if the state is not good, then there has to be some consequence in terms of what action you take, and the actions you take, because you could potentially trade off taking a suboptimal action now with respect to being in a good state in the future. So when I say good state, that has to be quantified typically using a value function, right? So they are related to each other. So that relationship is what we're going to establish through the formalism of Markov decision processes. Okay. Now, once we establish that, then we can talk about optimizing for the best policy, and you'll see that optimizing for the best policy could also involve, trying to get to good value functions, or trying to get good models, or directly, trying to get good policies. Okay, something like that. So, yeah.
So in 575, we learned hidden Markov model.
Yeah.
So Is that a part of this Markov decision processes? Because that was pretty similar too, like in terms of state and
Yeah, yeah, great question, Nisarg. So basically, as the name implies, there's a Markov modeling in there. The HMM corresponds to slightly different. So let me explain HMM right now, so that when we talk about MDP, you can see the difference, and we'll touch about it. Talk about it again. So hidden Markov model is about a modeling a sequence of random variables. Okay, so Markov models. So let me draw the diagram first. So what is this diagram? This is a diagram of a bunch of random variables. Okay. So let me put circles here. So think of these random variables y, y1, y2, y3, and y4. So typically most statistical models, not most, but a good chunk have some underlying joint distribution. Okay. So in HMMs, this joint distribution between a collection of random variables. Let's say these random variables are x1 to x4 and y1 to y4. Okay. By the way, HMMs are useful for a lot of things. Actually, in fact, language modeling that you've seen earlier, it's not HMM, but there was a Markov model involved there as well. If you remember, we were looking at the probability of a letter E given the previous letter was L and L and maybe one more L. Okay, maybe not one more L, but something like this, right? We were looking at character level model. So this is also called essentially a Markov model. But anyway, coming back to HMMs, the Markov modeling just means that the probability of, let's say, x3, pick a random variable x3, given that I have seen x2 and x1, okay, is equal to the probability of x3 given x2. In the sense that if I tell you what x2's value is, I shaded it, I should not have shaded it, but okay. All I'm saying is if you tell me, okay, actually maybe I should use this. Does this work? Yeah. If I give you x2, the values that x3 takes has nothing to do with what value x1 took. Okay, so that's the Markovian property here. Okay, so this is Markov model. The last two letters just correspond to this. Okay. Now, what could x itself be? X itself is a random variable. You can think of it as the true, for example, the true speed of the car. Let's say. So let's say x or the true position of the car. Let's say x1, x2, x3, x4. Each of the xi's is a two-dimensional random variable, which is just the xy coordinates of a car. Okay, let's say. Now, what are y1, y2, y3, y4? These are your sensor measurements. Okay, so just to give an example, so yi's are also R2. They depend on x2. So if the actual car is at location 10, 10 in some coordinate space, your sensor could measure it as 10.2, 9.9, right? So that's y1. So y1 is another random variable. So that depends on x1. Given x1, y1 will think of it as like adding a little bit of noise, and then that's the realization that y1 you see. Okay. Now, the hidden part comes in where it says where the model says that you have this bunch of random variables, but the only thing that you observe are the random variables which are below this line. So these are the only variables you observe. So you only see y's, y1, y2, y3, y4, which is the sensor measurements. Okay, you actually don't see where the true position of the car is. Okay, so in that sense, it's a hidden Markov model. So what is hidden is x1, x2, x3, x4. Let's say those random variables because they're not observed, and those random variables follow the Markovian property, which is this. Okay, that's a hidden Markov model. And it can be used for, I mean, it's, at least till about a decade ago, it was being used. Even as recent as half a decade, 5 years ago, it is still being used in parts of speech processing pipelines. So more traditional speech processing pipelines, like voice recognition, voice to text. They would use hidden Markov models as part of as basically language models. Okay. And you can use HMMs for actually I'm trying to remember, was it language model or acoustic model? Okay, so they were used in speech processing. And
and
whereas,
in those vacuums that do like a random random motion, maybe.
Um, so this is basically a time series model. All it's saying is that you have this time series of y1 to y whatever t or yt, because you're just saying that underlying these random observations is a Markovian sequence of x1 to xt. Okay, so it's useful in generally any time series problem, including language modeling. It's language essentially a time series problem because you're predicting the next word given the previous words and so on. Yeah, I don't know about the vacuum stuff that you're talking about, but
Yep.
that's what a hidden Markov model. So, I mean, the common thing is the Markovian nature, but we'll talk about, but you'll also see there's this, okay, here itself, I'll tell you a new terminology. This is called a process, actually a stochastic process. Sorry for the very messy notation, very messy way of writing there. But a stochastic process is nothing but a sequence of random variables, x1 to xt, or it could be y1 to yt. These are all stochastic processes, discrete time stochastic processes. Okay, so when you see the word process, just think of it as something to do with a sequence of random variables. Okay, something like that. But let's now talk about Markov decision process, and we'll actually talk about a most primitive thing called, or in this sequence, I guess a more simpler thing is called a Markov chain. We're going to talk about Markov chain, and then we're going to talk about what is called a Markov reward process, and then a Markov decision process, and pretty much they're all related to each other, and the way they are related to each other is the following, right? A Markov chain is nothing but a sequence of states or a sequence of random variables where transitions happen by themselves. Okay, if you're in a certain state, there's some probability with which you'll go to some other state naturally in the next time step. Okay, so that state transition, there's a state transition, and the corresponding sequence of random variables is called a Markov chain. You can add rewards whenever you go from state S1 to S2. Maybe there's some reward that emitted. You get a reward. Okay, again, it's still autonomous. It's just some sequence of random variables getting realized and some rewards getting realized. That's called a Markov reward process. But if you add actions to it, okay, now there's a sequence of random variables, but the jump from one state to the next state, if it's influenced by an action also that you introduce at every time step, then that becomes a Markov decision process. So I think this slide itself already tells you what these three objects are, but let me explain it a little bit more. So a Markov chain, as I said, is a sequence of random variables, which is essentially characterized by a transition probability function. Okay, so a transition probability function, P as S prime, is all it's saying is what's the probability of going to S prime given my current state is S. Okay, so think of the random variables S1, S2, S3. Okay, let's say the current happens to be current state is S. And what's the probability of going to next state being S prime? Because next state could be S double prime, S triple prime, some other numbers, right? Other things. Sorry. Okay. Wow. I think I lost something. But all I'm saying is this change from a random variable, a realization of a random variable to another realization, it just is characterized completely by a transition probability matrix. Okay, so because, for example, if you start from a state S, you know exactly which state maybe you went to state S prime, maybe from S prime you went to some other state S double prime, and so on. Okay, in the third time step and so on. Okay? So that's a Markov chain. And as I said, this PSS prime, you can also write it this way, right? You can actually write a matrix with the number of rows being the number of states and the number of columns being the number of states. Okay? So each row here is basically saying if I'm in state 1, what's the probability I'll remain in state 1? What's the probability I'll go to state little n, and so on. Okay, that's a cardinality of S is equal to n. So this is n cross n matrix. Okay, so each row is just a probability mass function. Given the current state, these are all the states I can go to, let's say all the n states, little n states, and they just correspond to a probability mass function. Okay, so here's an example of Markov chain. Let's say you're in a certain class, you autonomously go to class number 3 with probability 0.8, you go to sleep with probability 0.2, and so on. So there's nothing, we are just exogenously observing this. This just happens every time step. Okay, if you consider it from an observer point of view. And so if you have this Markov chain, let's say an example Markov chain like this, then you can always, you can start from some starting state, let's say class 1. Okay. So by the way, this chain has 3 classes, class 1, class 2, class 3, and a few other states, pass, pub, sleep, and Facebook. And some states don't have an outgoing arrow. Okay. So some states are essentially what are called terminal states. Once you sleep, then it ends the Markov chain. Okay. It stops the Markov chain. So okay, so if you start from class 1, maybe go to class 2, class 3 in one particular realization, maybe go to pass and then sleep. Maybe in some other sequence, you go from class 1 to Facebook, class 1, class 2, and then sleep, and so on. Okay, so these are all realizations that can happen, like time series sequences, right? Or if you think of language models, it's like sentences, essentially. Okay. And for this Markov chain, here is the transition probability matrix. Okay, it's just a matrix from every state to every other state. What's the probability with which I'll go there? Okay, so you can see there's a lot of zeros here, but there are some non-zero numbers as well, and you can see that the row sum is always 1. Okay, like 0.1 plus 0.9 is 1, 0.2 plus 0.4 plus 0.4 is 1, and so on. Okay, and this one is also 1. So that's Markov chains. Okay, those are simple. Now, Markov chain with rewards is called a Markov reward process. So MRP is can be described using a bunch of states, a transition probability matrix, and a reward function, and potentially also a discount function. Okay, a discount function is discount factor. Recall from some early slide, I said it's just a number between 0 and 1. It's just a additional parameter. You can ignore it for now. It makes sense for Markov chains which pretty much have no terminal state to keep on going. So if you keep on, let's say, adding rewards, for example, those numbers will blow up to infinity. So to keep them self-contained, contained, or keep them finite, you can introduce a discount factor. But there is no addition going on so far, so let's not worry about it. The S is a bunch of states. P is that usual transition probability matrix. Like here's an example. This is states 7 cross 7 matrix, right? Yeah. And R is the new object that we have introduced here on top of Markov chain, which is just what is the expected reward that I can get if I'm in a state S. So every state there's a number, there's a distribution associated with it, and the average of that is therefore there's a random variable there. So the expected value of that random variable is this number. So there's one number per state. So think of this as a function. Given a state, produces a number. That's the reward function. Okay. So that's Markov chain with rewards. What you can do with these rewards is the following, right? So you can say, you can compute the following quantity, which is that the following random variable, which is the total discounted reward from time step t. So let's say you have this Markov chain, and you look at the tth time period random variable. Okay, you're in state. It's actually you're in state st. Okay, so st emitted a reward, let's say rt plus 1. Okay, it emitted a reward. It went to some other state st plus 1. And then it emitted a reward rt plus 2, and so on. Okay, so that can happen all the way to infinity, right? If the Markov chain doesn't have a terminal state, as I said, terminal state just means there's no outgoing edges, like sleep has no outgoing edges. And then you look at the average of all these numbers, but the average is discounted by this discount factor gamma. Okay, as I was saying, without this gamma, if let's say each of the r is equal to 1. Okay, if you sum out sum of infinite ones, then of course the sum is going to be infinity. But if you introduce a gamma, and let's say gamma is 0.9, then the sum is not infinity. Okay, and you guys know how to compute the geometric sum, right? So this random variable gt is a function of all these random variables, rt plus 1, rt plus 2, all the way to rt plus r infinity, basically. It's called the return random variable. Okay, it's a total discounted reward from time step t. Okay, it's a number that you can compute for every time t. It's a random variable that you can represent for every time step t. And you can, since it's a random variable, it's gonna have its own distribution and average value and so on. Okay, but we are interested in its average value. So the value function of a state is going to be the long-term value. Sorry, the value function of state is going to be the expected return, or the expected return of starting from the state S. Okay, so basically the value of a state, is just the expectation of GT given that the current state is a little less. Okay. So that's so to understand what is a value function, you just need to know a Markov chain and a Markov reward process. In the Markov reward process, if all we're saying is starting from a starting state little less, you run the Markov chain. So let's say you start with the you clamp the starting state to be starting state or the teeth period, it doesn't matter. So S1 is equal to little less. From there onwards, you keep running the Markov chain. It'll keep going swiftly, changing from state to state based on transition probability matrix. It'll keep emitting some random variables. You take the average. Okay. If you repeat this, this Markov chain, simulation, or you can get a realization a few times, like this, right? If you have a Markov chain, you can get many sequences of states themselves, and based accordingly, they'll get a bunch of corresponding R numbers as well, right? For each state that you're in, so that means you have several realizations of the return random variable. Okay, you average it out. So that's this expectation here. Okay, once you get that average is the value of the being in that state. So what I've kind of brushed under the rug is we're looking at an infinite horizon problem, as if we are not thinking of some sort of a terminal state and so on. But if you're terminal states, you would slightly change the definition. But here, this is the most, I guess, simplest version of this. Okay, so this is the value of a state that you can compute the moment you have a Markov reward process. Now, so let me give an example. So let's go back to this Markov chain. The Markov chain, all we are doing is for every state, we're just saying, oh, if you're in the state, just pick up a reward of something. Okay, 0 reward for sleep. Maybe if you're in class, -2, class -2, class -2, and so on. And other states, some rewards. Okay. So if you do that, then for each sequence of states, it's a Markov chain. It autonomously keeps switching between one state to the next state at every time step. You can compute, okay, for every switch, what was the corresponding reward. Okay, and you can discount it. So here the discounting parameters happens to be 1/2. So you can do 1/2 square, 1/2 cube, 1/2 to the power 4, and so on. So if you do this, you can get a value. Okay, you got these values all the time. So let's forget about this last one. So all these guys started from the same state C1, and these are all the realizations of the values. You take an average of these 4 numbers. Okay, that's an approximation to the value of being in state C1. It's approximately the average of these numbers. Okay, the numbers above. Okay, so we understood in the Markov reward process, we can have have the notion of a value. Now we're going to introduce another, I guess a property about these values. Okay, a property about these value functions, and that is the following, which is that the value function can be decomposed into 2 parts. Okay, basically we're trying to get in this slide is that a value function can be written in a recursive way. Okay, so some of you have done programming before, might have heard of recursion, right? Where, for example, if you're solving for the Fibonacci, Fibonacci series, then what is it? No, let's pick a different example. Let's say you're solving for factorial. Okay, so a factorial for a factorial 5 is 5 times 4 times 3 times 2 times 1 and so on. So factorial for a number n is equal to n times the factorial of n minus 1, right? So you can call the same function again, right? So f of n is equal to n times factorial of n minus 1, right? And there's a base case where it's 1. So this is a recursion. This is a recursive relationship. Similarly, value function can also have a recursive relationship, and that can be seen by the following, right? So what we're saying is that the recursive relationship is that the value function is the some sort of a average of the immediate reward plus the value at some other states. Okay, so how do you do that? So you look at this. So you have the first. This is by definition, right? So value function is just the average of the return random variable, starting from the state little s. Now we know that the return random variable is just this sum, okay, going to infinity. We are assuming infinite horizon. Infinite horizon just means that this can, this Markov chain goes all the way, doesn't stop anywhere. Yeah, I mean, yeah, it doesn't have a predefined stop. It could have some terminal states. Okay. Now, so now this sum, you can take the gamma common, and then you can see there's still an infinite sum. Yeah, so you took the gamma common, so gamma squared became gamma here. Okay. Now this sum, okay, the sum inside the parenthesis is actually gt minus 1. Okay. Why is that? Because you can see, so gt minus 1 is going to be the return random variable, which corresponds to the sum of all the returns from t plus 2 onwards. Okay, similarly, just like gt, the sum of all the return random variables from t plus 1 onwards, right? So you can substitute this as gt. Okay, now from this step to this step, what's happening is you are pushing the expectation. So, okay, let me explain it a little bit more clearly. So you have this expectation over rt plus 1 plus gamma gt plus gt plus 1 given st is equal to little s. Okay, so this was the value function v of s, right? Now this expectation, let's focus on this expectation. This expectation is over all the possible sequences that are, this expectation is over s s yeah, s so st is given, right? So st plus 1, st plus 2, all the way to, whatever is all the way to whatever number, all the way to s infinity, for example. Now this expectation, you can write it as expectation because the first rt plus 1 only depends on st. So this is expectation of rt plus 1 given st is equal to s. By definition, so now this expectation is only with respect to, yeah. So, okay, I think I should write, yeah, I think this is fine. Plus the expectation of, let's take gamma out, expectation of gt plus 1 given okay. So expectation of gt plus 1 st is equal to s. Okay. So here I'm not done anything. I mean, I just broke the expectation into two terms. I mean, expectation of sum of random variables, sum of two terms is just the expectation of first term plus expectation of second term. Now, this guy is the, by definition, recall this is r of s, right? I mean, you don't have to write it explicitly, but this is r of s. Now, this guy, okay, plus gamma, what you can do is you can keep the expectation with respect to st out, okay, and then you can take the expectation with respect to the remaining random variables, st plus 1 onwards of gt plus 1 given st plus 1 is equal to some s prime. Okay. What I'm saying is this expectation is over a bunch of random variables. You can take this expectation, because it's expectation over several random variables, you can take some expectations first and then leave some expectations for later. Okay, so let's, first we broke down into two terms anyway. So this term, it doesn't depend on st plus 2, st plus 1, and all that. So this is fine. So this is just very clearly, this is just the expectation with respect to st. So actually, this is expectation with respect to this random variable only. That's the only randomness left. Okay, but this expectation, the second expectation here, that's that has all the remaining randomness still present, which is this underlying thing here. So this expectation still depends on st plus 1, st plus 2, and all that. Okay, so so this part is fine. I think I should not have written this. So this expectation is just the same as before. This is with respect to from st going to st plus 1, right? So let's say expectation with respect to let me write it. Yeah, st plus 1, and then st plus 2, and so on. Okay. So what I've done is there's a bunch of random variables, st plus 1, st plus 2, and all that. If you focus on the second term, I kept st plus 1 outside. And so, which means that condition on st plus 1 is equal to s prime, I'll have many such expressions here. Okay, and this expression is equal to v of st plus 1, okay, where this is capital S. Okay, and that's it. So this plus gamma times expectation over st plus 1 given st is equal to s. So this is a second term. So now let's come back to here. If you didn't follow, all I'm trying to say is that this value function at a given state is the average of the immediate reward rt plus 1, because remember we are at this value function is basically saying the value at a state of the state of the state s capital st is equal to little s is equal to the expectation with respect to the immediate reward plus the value at the future state, but the future state is a random variable. Okay, so why do we get this? Is by just expanding out the expectation as being expectation of several random variables. So you just instead of writing expectation with respect to the first random variable, second random variable, third random variable, and so on, several times writing the expectation expression, we have compressed it and as a short form written a single e. Okay, single expectation operation. So this is a key equality, okay? And you'll see that we can define what is called the Bellman expectation equation. We'll talk about this soon. You can define Bellman expectation equation, and it comes exactly from here, okay? We haven't even talked about RL problem yet. There's still, from Markov chains, we've gone to Markov reward processes. And even from Markov reward processes, we can talk about the return random variable and therefore the value function, and the recursion for the value function, which is what this slide captures. Okay, a recursion. So v of s, and there's the same function b, but a different evaluation, similar to this, right? Recursive function for the factorial function, which is being evaluated at a different number, right? Okay, so now let's come back to the same, the recursive equation above, which is v of s is the expectation of the immediate reward plus the expectation of the future value function, okay, whose argument is a random variable, so it's a random variable, is can also be written in this way. So v of s is equal to r of s, which is what I wrote here, okay, plus gamma times an average. Okay, so this is what I was writing here. So this plus gamma times plus gamma times this is nothing but gamma times sum over probability of going to s prime from s, taking action a, times v of s prime. Okay, sum over s prime. Okay, so that's this expression here, sum over s prime of probability of, okay, there's no action actually, sorry, in this Markov reward process. So it's just the average of all the states that you can get to and the values at those states. Okay, so all I'm saying is recursion is the value of the current state is the immediate reward plus all the states you can get to from s, which is s primes of, there are 3 different s primes and there are 3 terms here, the values of those states and the probability with which we'll get to those states. Okay, so that's a key recursive relation. So let's talk about Markov decision process. Okay, so Markov decision process is essentially a Markov reward process where the transitions are influenced by actions as well. So the only new quantity that we're going to introduce is the set of actions. Okay, so because there's this, there's set of actions, set of states, and all that. So that's why you represent it as a bunch of symbols here. So you already had states before. What we added is actions. We already had transition probabilities before, but now they are slightly changed. Rewards before, discounting as before. Okay, so what changed is this equation here, which says the probability of me going to new state S prime, being in state S and taking action A. Okay, this is represented by this compact notation, and this was exactly the same as the model definition we saw about half an hour ago, right? The additional part was this additional conditioning on AT is equal to A. Otherwise, it would be just the Markov reward process. Similarly, the reward function will also now be conditioned on A. Okay, condition the action. Okay, so if you come back to the running example that we had of a small Markov chain and Markov reward process, in the Markov decision process, what we did is shift the shift the states. So the states have not changed. The states could be are not named here. What's named here is that if you are in some state and if you take the action study, then you'll be again in some other state. Okay, some other state, and because you took the action study in this state, you'll get a reward. Okay, now and you'll reach some other state. And in other state, if you take the action study, you'll go into, I guess, the state, which is, the name is not given. Okay. Similarly, if you're in this state, and if you take the action sleep, you get into this state. Okay, so now you have actions which influence where you go. Okay, so that's essentially what a Markov decision process is. So let's see. So now that we've introduced actions, we can now talk about policies again. Okay. Now, what is a policy? A policy is nothing but a conditional probability which says, oh, if you're in state S, what action should you take? It could also be just a default action with probability, like for example, with probability 1, there's a specific action that you want to take. Okay. Now, the relation, now going back to the relation between MDP and MRP is that given an MDP, okay, a Markov decision process, as I said, just recall, the process is just a sequence of random variables. Decision just represents that you have added actions into the picture. Markov just means that the next state only depends on the current state and not all the previous states. Okay, so now an MDP, if you give an MDP as well as a policy, okay, if you give an MDP as well as a policy, if you recall, just specifies for every state what action to take. That means that if you give an MDP and a policy, you actually get the state sequence is nothing but a Markov process. Okay, and because we also have rewards involved, it's essentially nothing but a Markov reward process. Okay? So if you additionally give me a policy in addition to the Markov decision process, it's nothing but a Markov reward process. And for Markov reward processes, we've already seen what is the value of the state. Okay, and we've already seen the recursive equation for the state. Recursive equation for the value function. Okay. So the notation I've used here is the P superscript pi, which represents, for this policy, what is the transition probability matrix? If I tell you the policy, then we are only concerned with going from state S to state S prime. So the action is by default given by pi anyway, so that you don't get to choose that anymore. Okay, so that's why it's a Markov reward process. So we have changed the notation to P pi and R pi to say that if you give me a policy for an MDP, then this is a corresponding Markov reward process. And P pi is nothing but if there's any randomness with respect to actions times the probability of you going to state S prime given action A and being in state S. Okay, so being in state S and taking an action A, you land in state S prime. That times the probability that you would take action A is the probability with which you would go from S to S prime. Okay. Similarly, R pi of S is just the averaged out version of the probability you to take action A and the reward for taking action A in that given state S. So that's the relation. So what we did so far is just quickly come back to an MDP and say, how is MDP different from an MRP? The only difference is that for an MDP, if you specify a policy beforehand, then you get an MRP. Okay. And now what we're interested in, just to close up this part about MDP, is that we want to talk about the value function of an MDP. And more specifically, we're also going to introduce what is called the state action value function of an MDP. Okay. Now, so this section ends with us being able to say, oh, here's the Markov addition process. Here are the two value functions. And then next step, which we're going to discuss next week, is how to now optimize for the best policy. Okay, when we try to optimize for the best policy, one way to do that, okay, and to optimize for the best policy, we have to learn. Okay, just like in contextual balance, there was some learning involved. Okay, just like in multi-arm balance. So we're going to introduce those ideas. And one way to learn the best policy is through value functions, and also with the notion of exploration. Okay, so let's come back and define the value function. So the state action, so the state value function, okay, v pi of an MDP is determined by the expectation with respect to pi of the return random variable, given that the state is S. Okay, given that the state is S. From state S, you're just collecting all the rewards. Because I've already told you the policy, that's just a Markov chain. I mean, therefore, with the corresponding reward numbers, you just sum up the reward numbers. If you look at multiple realizations, average them out. Okay, that's this expectation, and that's the value of being in that state. Okay. The new item here with MDPs is the notion of a state action value function, or just the action value function. Okay. Now this object was not there for Markov reward processes. Now what is the action value function? It is the expectation of the same things, the same return random variable, where you start from the current state. The current state is S, or the starting state is little s, and you've taken a specific action A. Okay, so given that your starting state is S and you've taken a specific action A, okay, you're in state S, you took an action A, you'll, with some probability, you'll land up in some state S prime. From that state S prime onwards, so from that state onwards, you're going to apply the policy pi. Okay, remember there's a policy pi. Okay, so this is the action value function for a given policy. Okay, so all we are, so what, the only the kind of difference between this and this is that the pi of S is saying, starting on the state S, always apply pi of S immediately. So since I'm in S, I'll apply pi of S, which is some A, which will lead me to some state S prime, and so on. And I'll collect rewards, and I'll get the return random variable. I'll take its expectation. Now Q pi of S comma A is saying, oh, you're in state S, you get to choose one of the actions. So let me fix that action to be not pi of S, but some other action that, it could be some other action, it could be same action. I get to choose an action for the immediate time step. So let me pick an action A. Because of using S and, at the state S, I took an action A, I'll go to some other state. Okay, maybe let's call it S prime. From that state S prime onwards, I'm going to apply my policy. And from that S prime onwards, it's going to be a usual Markov reward process. Okay, so that's the distinction between these two. Okay, and you'll see that state action value functions are going to be very useful, in deep reinforcement learning that we're going to see next week. But also in a very classical algorithm called Q-learning, which will also cover early next week. Okay. I think since I'm running out of time, let me stop here. Are there any questions at this point? So I think just getting a sense of a Markov chain, and then a Markov reward process, and then a Markov addition process. And in between, we introduce a few things, which is the notion of a value function as the expectation of a return random variable, and some sort of a recursive equation which determines the which is related to this value function. And then towards the end, we have just described what is called an action. It's a state action value function, okay, or just the action value function. So are there any questions about this? So we will, from this slide onwards, we're gonna visit it next time. Okay, good. If there are no questions, we will end today. Yeah, if there are questions, just ask it on Slack, or use the teaching resources. Yeah, see you next week.